2023 by NASA's OSIRIS-REx spacecraft. What's really exciting here is that the discovery of an environment that would have allowed for these molecules to flourish were also seen. But more on that soon. This is your chance to interact with NASA experts and have your questions answered in real time. So send them in using the hashtag AskNASA in the comments wherever you're watching. In September 2023, NASA's OSIRIS-REx spacecraft returned to Earth carrying material it collected from asteroid Bennu. One reason Bennu was selected for sample return was due to its composition. After initial study by the spacecraft, we found the asteroid to be rich in carbon-based molecules like organics, which is the stuff of life. Bennu is also a primitive asteroid that serves as a time capsule for preserving materials from the dawn of the solar system. Since the sample has returned, scientists have been studying the captured materials in labs on Earth. Now, their findings show that Bennu comes from a wet world that formed in the coldest regions of the solar system, likely beyond the orbit of Saturn and nearly 4.6 billion years ago. Scientists were surprised to find that the asteroid sample held such a complete library of minerals that precipitated from the evaporation of salty water, many of which are similar to minerals found from dried, briny lakes on Earth, like Lake Searles in California's Mojave Desert. We are keeping an eye on the questions pouring in online, and we'll bring them straight to our experts live on air later on in the show. We also have experts in the comments standing by to answer your questions in real time. So let's jump right in. With us now is Dr. Danny Glavin. He is the OSIRIS-REx Sample Organics Lead and Senior Scientist at NASA Goddard. We also have Professor Sarah Russell. She is a cosmic mineralogist at the Natural History Museum in London. Thank you both so much for being here with us today, and congratulations on the discoveries in the sample.
Exciting times.
It really is. So before we jump into the exciting times, can you tell us a little bit about your roles? Danny, why don't you go first?
Yeah, so I'm Danny Glavin. I work at NASA's Goddard Space Flight Center, and I'm leading the Sample Organics Analysis Team, which is a group of about 60 scientists from around the world who've been looking at these pristine, precious samples from space. It's just amazing.
And Sarah?
So my name's Sarah Russell, and my day job is looking at meteorites in the Natural History Museum in London, but I've been part of the mineralogy team, which again is a team of scientists from around the world who've been looking at what Bennu's made of.
Very cool day job. Thank you both so much for being here with us. So let's get into the main topic of today's show, and that is the asteroid sample brought to Earth by the OSIRIS-REx spacecraft. Now, there are two big things here, right? Scientists found the key ingredients for life in the sample, but they also found an environment that is really conducive to fostering the type of chemical reactions that we know produce living things. So that's huge. Sarah, Danny, can you both explain to us really the significance of these findings, but also why together they mean so much?
Yeah, so when we looked at Bennu, we were expecting it to be full of water, and it is. So it's made mostly of clay minerals, which capture water in their structure. But what we weren't expecting to find was that it also contains tiny minerals of salt. So that includes sodium chloride, which you use on your chips.
Table salt?
Yes.
Oh, cool.
And also carbonates and sulfates and phosphates. So we found this whole range of different salty materials, and we think that these formed from a pod of water or pods of water that would have been under the ground of Bennu's parent body. And this water would have slowly evaporated away to leave behind these salts. But this salty water is a really exciting environment because that's where you have the potential to be able to make organic molecules.
And Danny, okay, with the organics.
Yeah, so I mean, one of the incredible findings here is that we found literally the chemical building blocks of life. We found 14 of the 20 amino acids used to build proteins, and all 5 nucleobases that make up the genetic code in DNA and RNA. And what's exciting is the combination that we're finding these chemical building blocks, but also these salty brines. And these environments are like places that we think life could have started on the early Earth, in these evaporating salty lakes. So these are just incredible samples to look at the prebiotic chemistry that may have led to life on Earth.
And so to focus on these molecules you just mentioned, so we found the building blocks of proteins, we found the building blocks of DNA and RNA. You know,
Correct.
Have we found these before? What's the significance in this discovery?
Yeah, so we actually have found a lot of these molecules in meteorites. I've been looking at these for the last 30 years. But one of the big frustrations for me with meteorites is that they've been contaminated. You know, these things fall through the atmosphere, they get heated, they hit the ground, they're immediately exposed to terrestrial contamination. And so you're never quite sure if what you're looking at is real. Well, with Bennu, we have samples now, 4.5 billion year old asteroid samples that were protected by a heat shield coming in, so it didn't experience the heat. They were protected from Earth's biology, contained, and we're finding these building blocks. So we have higher confidence in these results now. We can believe them. We trust that what we're looking at is extraterrestrial organic matter.
And it's out there right now,
Yeah.
which is so cool to think about. So Sarah, can you actually take us back now, like almost 4.6 billion years back to Bennu's parent body? What have we learned about that environment now from these samples?
Yes, so Bennu is like a time capsule from which we can learn about the whole 4.5 billion years of solar system history. And we think that Bennu formed probably in the outermost part of the solar system, and everything in the solar system condensed from a cloud of dust and gas. So most of it went in to form the sun in the center. But then this material also condensed to form the planets and also the minor bodies like the asteroids and comets. So Bennu would have formed from this dusty cloud of material, which would have included ice as well. And after it formed, the ice would have melted. It would have been gently heated by a little bit of radioactivity that was inside the body. And so the ice melted, and that then interacted with the rock and produced this whole new suite of minerals that we see today. So that was Bennu's parent body. Then at some point, it also got moved, ejected into the inner solar system, first the asteroid belt, and eventually to the near-Earth place where we see it today. And what we see today is basically a rubble pile asteroid. So Bennu's quite small, it's only 500 meters across, and it's basically made up of boulders that are just gently sort of stuck together. So these are just remnants of impacts that went into its original bigger body.
And so, Danny, how could these building blocks have arrived on Bennu?
Yeah, informed.
Yeah.
I mean, so we just heard from Sarah about the melting of these ices. And one of the really interesting things that we found, actually this was a big surprise, is that the Bennu samples have a lot of ammonia. Ammonia is the stuff you smell when you clean your windows, right?
Yeah.
With the spray, it's pungent. But ammonia is also an important building block to form amino acids in nucleobases. But it needs water to do that, right? So the ammonia can react with things to make these amino acids. So the fact that we're seeing these brines, melted liquid water, and we have these high ammonia concentrations is really, again, pointing towards an outer solar system origin where the ammonia ice was stable. And again, this environment where we can get this really complex organic chemistry because of these liquid brines.
Yeah, absolutely.
This is so fascinating to think about. And to provide some context to these discoveries and what they mean, here's what you need to know about the molecules of life. All right, so we got to break down on the building blocks of life. Sarah, now let's break down this environment. You know, I understand that there was mineral evidence of this briny, salty liquid for Bennu's parent body, which could have been this perfect broth to cook up these molecules of life that Danny's been talking about. How do we know that? Have we seen this anywhere before?
Yes. So when we saw this whole sequence of salts, it reminded us a little bit of lake beds on Earth. So like Searles Lake in California, where the lake itself has evaporated away and left behind this whole sequence of different minerals. And so this was a great analog for us to compare to Bennu, because we found a lot of exactly the same minerals. So this really helped us kind of visualize what was going on inside Bennu.
That's great. And I mean, Danny, we couldn't have really gotten this kind of analysis, right, unless we had these samples back here on Earth.
Oh yeah, there's no question. I mean, part of the power of these sample return missions is that you can bring these samples back and you have the world's instruments, right, to work with, state-of-the-art instrumentation. We did make measurements at Asteroid Bennu, and we had hints that there were clay minerals and water. We even had hints that there was organic carbon present on the surface, but we didn't know the form. We didn't know if these were amino acids or other chemical building blocks. Now we know, and that's because we have these samples in the lab, and we can use state-of-the-art instrumentation to analyze them.
And also these salts, they're very, very delicate, and if they came in a meteorite and became exposed to the atmosphere, then they would quickly dissolve away. So it was really important to have this very pristine sample that's been beautifully curated at the Johnson Space Center in Houston and kept in a nitrogen-only atmosphere and not being exposed to the Earth's atmosphere.
This is so fascinating, and so I'm going to pause because we've got a ton of questions coming in from our viewers online. And if you are just tuning in with us, remember you can submit your questions into the comment stream wherever you're watching by using Ask NASA. So let's jump into our first question. We have Freedom on X, who wants to know, where did these ingredients come from in the early solar system? Sarah, Danny?
Well, I can talk for the inorganic ingredients. So all of the elements that make up Earth, apart from the hydrogen, were made inside ancient stars that were ancestors to our own. So there's this whole incredible story about how we got to be on...
We really are star stuff. That's amazing.
Star stuff, exactly. So at the beginning of, you go back to the beginning of the universe, the Big Bang made a load of hydrogen, and that formed into stars, and they were factories for all of the other elements that we have. So ultimately, that's where this stuff came from. As millennia went on, more and more elements were created, and dust was formed around stars that was floating around and eventually became part of our solar system.
And Danny, when do the organics come into play
so
here?
this is actually an interesting question. We're trying to tease this part of it out, but it turns out that some of these ices, so you had this disk of ice and dust, you can get some chemistry happening on these ice grains, forming simple molecules, formaldehyde, and simple, nothing as complex as we're seeing in Bennu. But these ices, again, they get incorporated into the parent body, and then you have this radioactive heating, which can drive this additional chemistry, so you can form more complex structures like the amino acids and the nucleobases that we're seeing. We even have evidence that some of these ices may have come from the interstellar medium, a different solar system, and were swept. Yeah, I mean, so it's actually a very complex story. But the idea is that we started out with very simple compounds in the beginning, and then we developed this complexity with time.
And so my next question is from a user on Twitch who asks, what tests did you run on your samples and how long did it take? So I think this is a great one for both of you, because did you both run different tests?
We did.
Okay.
Who do you want to go first?
Very different.
All righty, cool. Well, let's hear about it. Sarah?
Yes, so what we did was we analysed the Bennu sample grain by grain. So the first lot of sample we got was basically kind of fine grain, like the grain size about pieces of sugar. So really tiny. So we'd pick up each little grain with tweezers, and first we CT scanned it. So this is a way, like the CT scans in hospital, you can look at the inside structure of a grain, and then we looked at it on the electron microscope, which gave us the chance to look at what minerals were there and how they interacted with each other, so we could tell which one formed first and which one formed after. So that helped us build up this story about Bennu.
Wow. And Danny, what about your side?
Yeah, so we made Bennu tea in our lab. We literally took some of the Bennu samples and put them in water, sealed them up, heated it at 100 degrees Celsius, and boiled it, and extracted the organic compounds, just like making tea. And then we analyzed this liquid with a variety of different mass spectrometer techniques, and these basically measure the mass of each organic compound to very high precision. And from that, you can identify what the molecule is. And actually, in this tea, we're finding a very complex soup, over 10,000 nitrogen-containing organic molecules. So we're literally just scratching the surface with these detections.
Is that unheard of?
It's
or?
We've seen this in other meteorites before, the complexity. But as I said, we're just getting started with these Bennu samples. It's going to take a lot of time to figure out what all these molecules are.
And so, Sarah, I know y'all had the samples at the Natural History Museum in London, right? But these samples have been sent all over the world. Is that correct?
Absolutely. We're part of this huge team on, is it 4 continents, 5 continents?
I lost count.
Okay, on most of the continents anyway, yeah. And we all have been working together, so we're having lots of telecoms to update each other on our results. So it's been one of the amazing things about this mission has been being able to work with these people all over the world.
That is so cool. And so, okay, I have our next question from Gold Eagle on YouTube, who wants to know, is this the first time that an asteroid has been found to have amino acids? Danny?
So no, actually the first sample, so the Hayabusa mission, which was a JAXA, Japanese Space Agency mission, brought back a tiny amount of sample from asteroid Itokawa. And we actually found a few amino acids in these tiny grains that we showed were non-protein amino acids and indicating an extraterrestrial origin. And then more recently, Hayabusa 2, the second Japanese mission, returned samples from Ryugu, about 6 grams, I think, or so, of material. And again, some of these amino acids were also found in those samples. So no, this isn't the first time. We are seeing a greater diversity of organic compounds in the Bennu samples, so that's pretty exciting. But I think really it's this ability to compare. We now have 3 asteroid samples.
Yeah.
And the science, really, the value here is being able to compare these samples to one another.
Well, I mean, this is a really exciting time to be in y'all's field of work.
Oh, absolutely.
And so that's amazing. Sarah, I have a great follow-up for you. Brad on YouTube asks, were there any discoveries of unknown substances in the asteroid? I know earlier you talked about knowing there was going to be clay.
Yes.
But,
there were some minerals that have not been seen in meteorites before, but have been seen on Earth, like sodium carbonate, for example, which is a mineral called trona. And then I think maybe what might be unique is we found a particular phosphate. It's a sodium magnesium phosphate, which is actually fairly abundant in Bennu, and we hadn't seen that before. So subsequently, it has been found on Ryugu and in a few meteorites as well. So it's not only found in Bennu.
any surprises for you, Danny, in y'all's analysis?
So we talked about the ammonia
Yeah.
surprise. So the ammonia levels were really high in the Bennu samples, about 100 times what you might find in your backyard soil, higher than what we found in Ryugu and higher than in most meteorites. But again, the fact that we're seeing these building blocks in all of these samples, right, suggests that this stuff is widespread.
Yeah.
I mean, these building blocks are not just limited to Bennu; they were all over the solar system, and I think that's just the idea that these things could have led to life not only on Earth but potentially elsewhere. That's what's getting me real excited right now.
Yeah. It is really exciting, and for the brines as well, we think we see these in other places in the solar system. So the moon of Saturn, Enceladus, has got plumes coming out of it that we think may be similar to this salty brine. And the biggest asteroid in the asteroid belt, Ceres, has got some white patches that we think might be salts as well. So absolutely, we think these things that we're seeing on Bennu, we might be seeing across the solar system.
And just to follow up quickly, we're also seeing the ammonia.
Oh, wow.
Ammonia salts on Ceres and in the Enceladus plume. So you have the again,
Yeah,
the raw
the whole
ingredients for
thing.
some of these
Yeah.
building blocks. So, yeah.
So I have a question from Zugard on X who wants to know, what is the likelihood of contamination before mission launch or analysis? Danny?
You want me to take that? Or you start?
I'll start and you carry on.
Okay,
Yeah, so contamination is something that was really important to us to try to keep to a minimum, and it's something that we have been tracking really closely throughout the mission, because one of the really important things was to try to get back a pristine sample, and to so we put all sorts of things in play to make sure that that happens, including having what we call witness plates, which are witness whatever the asteroid witnesses, so we can monitor them and see if they've become contaminated. So there's several things in place to make sure that we keep the contamination to a minimum, and where contamination happens, that we understand it so that we can then remove that from our analyses.
Yeah, I'll just follow up and say, it's impossible to keep something perfectly clean. We're sending a spacecraft built by humans into space, and it's impossible to completely eliminate contamination. But as you said, we've got witness plates to track it through all stages. My colleague Jason Dworkin was the contamination control lead, and he spent a lot of time working with the engineers, making sure we got to have this witness plate here, and we got to analyze it. And we were actually tracking the amino acid contribution on these plates through assembly, and didn't find much. Even something like nylon, that's a source of amino acids. And so there was a big push to just eliminate nylon completely.
Right.
Don't let the sampler head touch nylon. And we succeeded, actually, in making these pretty big changes to do that. And we're reaping the benefits now, right?
Yeah,
Yeah,
absolutely.
I understand. Didn't we build whole new sample analysis labs for these samples on Earth?
Well, there's a new curation facility
yeah,
that was built
exactly.
especially for OSIRIS-REx. So, yeah, absolutely.
Thank you both. And so our next question is someone on X who wants to know, did the samples include polypeptides that were chirally pure? So I think this one's a little technical.
Not for me.
Sarah? Yeah, that's an amazing question. So let's step back a little bit and talk about chirality first.
Okay.
So amino acids can come in two forms, just like your hands, and they're non-superimposable mirror images. So if you try to take your hands like this, you see my thumbs are sticking out, right? And so amino acids have that chirality, handedness, mirror image forms. All life on Earth is based only on the left-handed form. And we still don't know why. This is actually a big mystery, because life could have evolved with right-handed proteins, and it could have functioned just as well. So big mystery in the origin of life. To get at the question about peptides, so peptides are actually chains of amino acids. So take two amino acids, link them together, they form these long chains. And indeed, life, biology on Earth, is predominantly the left-handed form of these peptides. Now, we haven't found any peptides yet. We're looking carefully. We have a much larger sample now, so we're looking for these, that we call them polymers or peptides. And yeah, if we find them, absolutely, we'll be measuring the chirality, no question about it.
And Danny, I've got a good follow-up for you. It is one of our followers on X who wants to know, did you find other basic building blocks of life that have shown up in the sample or meteorites?
Do you want to talk about the phosphate?
Oh, yeah, we could talk about the
let's
phosphate
talk about
here,
the
yeah.
phosphate.
Yeah, so one of the reasons we're really excited to find phosphate in Bennu in quite high proportion is because phosphate's also really essential to life. So it makes the backbone of the DNA molecule.
Cool.
So it's really cool that these brines not only could have helped the organic reactions go along, but also when asteroids like Bennu hit the Earth, it would have delivered not only the organic material and the water, but also this other bioessential material like phosphate as well.
That's great. That's incredible. And so one thing I want to clear up as well, in this finding, we have found the key ingredients that life needs, and we have found the broth that could, spark the chemical reactions for the emergence of life, but we have no evidence that those
We haven't seen the spark yet.
The spark is not sparked.
No.
And
Yeah.
so,
Yeah, we haven't seen any life yet.
yeah. Well, it sounds like we've got a lot to look forward to, though, in these samples as well.
Absolutely.
So we actually have, okay, we were just talking about chirality and the handedness of molecules. We have Peter on YouTube who wants to know, why did these molecules go left? Which now we see that they can go left or right, but why? What was the assumption, I guess, before these new discoveries?
So it was Peter.
Yeah,
that's a great question. I mean, and this is really the million-dollar question that we're still trying to work out. Now, prior to this mission, we had some evidence from meteorites that there was this excess of some of the protein amino acids, the left-handed form, up to 60% more in some cases of the left-handed. So, actually, I was personally expecting when we brought these Bennu samples back, because it had a composition very similar to these meteorites, that we would also find left-handed excesses, but we didn't. You know, we found that they were equal mixtures, and you know, when I saw this, I was actually kind of depressed.
Yeah, my life.
I've been working on this for 20 years, and now let's just flush it down the toilet. I mean, that's honestly how I felt. But again, this is why we explore. This is why we do missions like OSIRIS-REx, to get closer to the truth. And you know, again, this is, you know, early days. It's one sample. We're going to be working on other samples to look at chirality. But right now, I think we can say that the origin of we call biological homochirality, left-handed base protein life, it's still a mystery. Yeah.
And I don't know if you mentioned this earlier, but what chirality does life on Earth take? It is mainly left-handed, right?
So it's left-handed amino acids and right-handed sugars that make up, you mentioned the phosphate, the sugar phosphate backbone. So it's actually left and right. So all you left-handers out there, we're not, you know, dominating the universe. So right-handers have a role too in the sugars.
Okay, great, thank you.
Yeah.
Sarah, I got a good question for you. We have Rashi on YouTube who wants to know what was the age of the sample collected, and how do we know that?
Oh, that is a great question. So we can age date things using radioactive isotopes. So there's certain isotopes, for example, uranium is a radioactive element, and it decays through a series of intermediaries to lead isotopes. And by looking at how much of these lead isotopes have built up, we can say how old it is. And the age dating of the components of Bennu is still a work in progress, so we're still working on that, but we think it's likely to be the same age as similar meteorites that we have in our collection. So that would put it right at the beginning of the solar system, so 4.5 billion years or older.
Wow. I mean, it's crazy to even try to think about a time scale that long ago.
Yeah, I mean, anything older than the Earth, it's like, wow. I mean, it really is. The fact that we have materials, you know, pristine materials that were that old, and we can actually look at this chemistry in this environment before life even started, it's incredible. We can't do that with rocks on Earth, right? They've all been processed by plate tectonics and the heating. That chemical record on Earth has been wiped out. And so we're getting that now, that prebiotic record with Bennu. It's incredible.
It is incredible. It's a real privilege to look at this material that's older than the Earth itself.
Yeah. Danny, I have a clarifying question from, you know, a conversation we were having earlier. Someone on YouTube asks, have they found any living organisms on any meteorites?
The only living organisms on meteorites are from the Earth.
Yeah.
And if anyone knows otherwise, let me know.
Yeah.
But yeah, that's the problem, right? Is that these meteorites, as soon as they hit the soil, you know, hit the Earth, that they become rapidly contaminated with biology.
And Sarah, I think you were touching on this a little bit earlier, but Adam on YouTube asks, with these findings, how confident can we be that other bodies in the solar system, you know, contain these organics or these environments that might be conducive to cooking them up?
So we're becoming increasingly confident that these are likely to be really widespread processes, because we do see some evidence for this on other bodies like Enceladus, and water is a very abundant material in our solar system, and so is organic material, and so it just makes sense that if it happens on Bennu, it's likely to happen across our solar system.
Yeah, and even, you know, other solar systems. So I talked about these ice grains that could be from the interstellar medium. there's really nothing to suggest that the basic building block chemistry is unique to our solar system. So this is exciting, as we go explore exoplanets, we should be looking for life there as well.
Definitely.
So we have Universe on YouTube who asks, other than chemicals that contain life, so I think they're talking about like organic molecules, what was the rarest chemical or substance you guys have found on the asteroid sample?
We have found, lots of fairly rare substances in Bennu. So one of the exciting things for me was finding material that was floating around in the protoplanetary disk before Bennu's parent body accreted. So we do find some tiny grains of minerals like hibonite and spinel, for example, which are very, very rare in Bennu, and we think these may have been among the oldest grains, and they survived all of this water reaction.
Wow.
So they can give us a glimpse back to what the protoplanetary disk was like at that time. So that's sort of my favorite rare thing.
Anything rare on the organic side?
Well, actually, I was going to say no, but now that I think about it, we actually found 33 amino acids in total detected in the Bennu samples. 14 were protein amino acids, but the other 19 were non-protein, not found in biology. And in fact, we're finding some amino acids that don't even occur naturally on the Earth. They truly are rare, some of these non-protein amino acids. So,
wow.
Have you seen them in meteorites before?
We have seen them in meteorites, but I just wanted to make that point. We're seeing the building blocks of life, but we're also seeing these other similar compounds that, for whatever reason, weren't used by life. So that's a whole another mystery in and of itself. Why did life choose those 20 when there were hundreds of amino acids available?
And so are the amino acids you're talking about, from what we know, only formed in space or material that has come from space?
Well, we can make them in the lab, of course. But the fact that some of these really rare non-protein amino acids were formed in these is really an interesting question. Why? Of course, biology has taken over on the Earth, and so that's why the 20 are the most common ones here. But it's really interesting to think that a lot more was probably available early on in that prebiotic soup. And why did life choose the 20? I don't have the answer to that.
Yeah. So much had to have gone right, it seems like,
absolutely,
for us to be here today.
Yep.
So I have Ian Riddle on X who wants to know, could it have been Bennu's parent asteroid that struck Earth 65 million years ago? It's a tough one.
That is a tough one. So there is some evidence. So this is the impact that crushed into Earth and was responsible for killing the dinosaurs and most of other life on Earth at that time. And there is some evidence that it's an outer solar system body, so it may have been something related to Bennu, but we don't know. I believe we don't know enough about it to know exactly whether how similar it was to Bennu.
Yeah.
Yeah, I'll just make one quick follow-up to that. Actually, there's these boundary, they call it KT, maybe it has a new name, but that's 65 million year old boundary. We actually found some of these rare, I call it the non-protein amino acids, alpha amino isobutyric acid. I know it's a mouthful, AIB, but that was found in high concentrations along with iridium at that layer. Again, suggesting that, one of these asteroids, possibly like Bennu, hit. And not only killed the dinosaurs, but delivered amino acids to the Earth. So, yeah.
Wow. Well, I have a great question for both of you. It's from Coin on Twitch, who wants to know, when you were kids, did you one day think that you were going to be analyzing life-related samples from space? So.
For me, no.
Yeah.
I mean, I will be honest with you, I was never very into biology, but what I was interested in was geology, so I used to collect rocks, and I was also into space, so I loved watching things like this. I loved hearing about NASA missions, and I really kind of devoured everything that was going on in space exploration. So I feel really lucky now to be involved in this space mission, and it's been a sort of exciting twist for me that our work has kind of put us in the direction of thinking about the ingredients for life. So that's really fun.
Yeah, what about you, Denny?
Yeah, the same. I mean, I I couldn't have dreamed of being an astrobiologist. I didn't even think I knew what that was as a kid, but I did love rocks, just like you. And I drew, pictures of aliens and the space shuttle, and so yeah, maybe not a big shock that I, am now studying space rocks. But actually in college, I got into physics, and I thought I wanted to study black holes, and then something big happened. In 1996, there was an announcement of the Allen Hills 8401 Martian meteorite that was found in Antarctica, reported to contain evidence of Martian life. And I think at that moment, that changed everything for me.
Yeah.
I'm like, just the idea that meteorites could be transporting the building blocks, seeding, life throughout the soil. I was hooked. I'm like, I've got to get into astrobiology now. I got to study these rocks.
Wow.
I got to look for evidence of life. And so, yeah, I hope some of the viewers are finding inspiration from this announcement. And, maybe this will encourage you to get into this field. We need more people working on this.
Yeah.
Yeah.
Absolutely. I mean, it's answering some of humanity's biggest questions. And so one thing that I think is really cool about this mission is that we are saving some samples, right? Some are being specially, contained for the next generation of scientists and astrobiologists and mineralogists to sample with, cutting edge technology as well.
Absolutely. So we've only used a tiny fraction of the 120.
Do you happen to know how much of the fraction has been used?
Oh, God.
No.
Less than
It's okay.
%?
Yeah.
I don't know. It's very...
Our friends in the comments,
You got us.
our experts in the comments can help us out with that one.
Yeah, I'm not great with numbers like that, but still most of it is available, and that's fantastic. And some of it's being deep frozen, so kept at cryogenic temperatures to make sure that it stays super pristine, and it'll be available for scientists in the next years and the next centuries even.
Wow.
To answer their own questions.
So the one number I do know
Yeah.
is that more than 70% of the mass return, and we returned about 4 ounces, 120 grams, more than 70% of that will be saved for the future generations. So like you mentioned, the one we've got a sample, 7.5 grams, sealed up in a freezer, minus 80. And this might be opened 50 years from now, like they recently did with the Apollo samples.
Oh, yeah.
I wasn't even born when they collected those samples, and now, we're analyzing them. So the same will be true with these Bennu. There'll be people that aren't even born yet that will be studying these samples with even technologies that don't even exist, answering questions they didn't even know how to ask. I mean, it's the gift that keeps on giving.
It really is. Wow, that's beautiful to think about.
Yeah.
So back to this sample, we have Angel Lady on Twitch who asks, could you explain the process of how the OSIRIS-REx spacecraft collected and returned this sample?
Right. Okay. So the OSIRIS-REx spacecraft spent 2 years getting data from Bennu, going around it and getting a fantastic sort of view of what the asteroid was made of. And then we very carefully selected which site we'd like to sample. And on the day of the sampling, this arm came out, touched the surface. It's called a touch and go mechanism. Here's a video of it on the screen. That's fantastic. So the
I believe that's a live video, like an actual video. From
that is an actual video. And so when the spacecraft was designed, we were expecting it to be quite a hard surface, but actually it's very, very porous. It's like a ball pit, and the arm went straight through and managed to sample this fantastic collection of material from the surface and the subsurface, and then retracted back with its goodies.
Yeah. What a cool concept for a mission. So we have
cool.
Sam on YouTube who has a great follow-up to this. They ask, do we know if the asteroid is hollow, or was it really just this like big rubble pile that if you keep going into, there would be no end?
Yeah, I mean, it's definitely not hollow. It's not like I don't know.
Shell?
A shell.
A shell.
It's a rubble pile, so it's these loose, boulders that are loosely held together. When we plunged in, that was totally not predicted. I mean, fortunately, the backway thrusters, they were on timers. They got us out of there. Because if not, Bennu would have swallowed the spacecraft.
Wow.
I mean, it was actually a very, very scary moment. But everything worked out. And so, yeah, it's not hollow, but there are a lot of voids, void space in between these boulders. Yeah.
Was there anything that, I mean, you said it was a scary moment. Was there anything unexpected with this mission, this sample return?
what wasn't.
Yeah, there were lots of things expected. So one thing that we found is that Bennu is what's called an active asteroid. So every so often there'll be like a shoot of the gas coming off from the surface of it. And that was kind of exciting, but also scary because we were worried.
The health of the spacecraft.
Yes, exactly.
Yeah.
Exactly.
They were moving slow.
Yeah. Yeah, so there was that. And then when the sample mechanism came back, it was slightly leaking, so some bits were coming out. And so that meant it had to be stowed really quickly to make sure that we could keep the sample safe.
Yeah, that was, you remember the images, the video of particles coming out of the TAGSAM head. I think, there it is.
Oh, yeah.
Well,
And I'll never forget, I remember the PI, Andre Loretta, saying at this moment, oh my God, every particle is somebody's PhD thesis.
Yeah, we're losing.
And so, it was intense. But again, we got 120 grams back, more than 2 times
Wow.
emission requirement. So we still got a bounty of material.
Our next question is from Samus on Twitch, who asks, what are the next steps regarding this research and findings?
Well, for me, one of the big questions is we know that there were these brines, but we don't know very much about the timings. So we expect that the brines were formed very early in the solar system, maybe just a few million years after Bennu's parent body accreted, but we don't know for sure. So I'd love to know more about the whole timing, about the alteration of Bennu. That's my big ask over the next few months.
And what about you? What about your research?
Yeah, so we talked about going from the building blocks, right, the amino acids to more complex structures like proteins or nucleic acid-like molecules. And so we do now have a much larger sample of Bennu, about 6 grams, that we're going to use to look for these more complex polymers, the peptides, the amino acids that form chains, and maybe compounds that look more like DNA, more nucleotides. So we'll see what we find. I think that if they're present at very low concentrations, which is why we need more sample to find them. But we're going to look with the best instruments we have on Earth to look for these,
And will both of your 2 teams be continuing your research, or is this analysis that might be done by another group of scientists, or will you still have your hands on the samples and be looking at them?
Well, the mission finishes in September 2025, so at that point the sample analysis team work is done, and we give the samples back to the Johnson Space Center. But at that point, or even at the moment, anyone can request a sample to use for their research. So if we have outstanding questions, we can just put in a request to have a bit of sample to work with.
Wow.
Yeah, it's pretty exciting.
These
samples are literally
open.
open.
Can request them.
Anybody in the science community that has a technique and a good idea, and has demonstrated on meteorites, right? Can ask NASA Johnson Space Center for write a proposal and request sample.
That's wonderful. Our next question is from Cookie J on Twitch, who wants to know, from these findings, what we've learned, does that mean that the early building blocks of life that started on Earth could have come from asteroids? Danny?
I think we can't rule that out. This is really the big theory. We call it the exogenous delivery theory. Actually, there's a theory that life on Earth started because of asteroids like Bennu and the fragments, meteorites, interplanetary dust particles that delivered this organic material, the building blocks. So I think that the analyses that we've done at Bennu is certainly adding more credibility to that theory. But the bottom line is we don't know. Right? We can't go back in time 4 billion years ago to see exactly how it started, but it's looking pretty good that at least asteroids had some role in bringing the building blocks to Earth.
And Danny, I have a follow-up from Ivan Levins on X, who asks, so the evidence is leading towards us not being alone in the universe. What would you say to that? This again, these chemical building blocks of life, the stuff that makes you and I up, all our viewers, we're all made of the same stuff, is being formed in space and is spread throughout the solar system. And not only the organic compounds, but the environments, these briny, salty
fluids were there to even drive more complex chemistry. So I'm definitely becoming more optimistic in our search for life, even in our own solar system, because the building blocks they're everywhere.
And Sarah, my next question is for you from one of our followers on X, who wants to know, do experts believe that these organic materials or these environments reside all over the asteroid belt?
Yes, so one of the reasons we chose Bennu was because we thought that it was going to be rich in water and carbon, and it is. So it's a type of asteroid called a C-type, or carbon-rich type. And that sort of asteroid is actually pretty common around our solar system. So absolutely, these things we expect will be pretty widespread across our solar system.
And we have Kay Powers on Twitch who asks, one, was there water on the asteroid on Bennu, which we know that there is, but two, is it common for asteroids to have water on them?
It is pretty common, yeah. So, so this sort of asteroid, the C-type asteroid, one of its characteristics is that we think it does have water. And that's something we can often see even from space because it has a particular signature that only water has. So we can see that many of these asteroids do contain water. Not liquid water.
Oh, that was going to be my follow-up question.
No, but water in the form of clays. So basically they're like a ball of mud.
But there certainly are environments in the outer solar, we talked about Enceladus.
Oh, yeah, sure.
These are icy moons that we believe have oceans.
Oh, for sure. I was just thinking about the asteroids.
Maybe even Sirius.
Yeah.
And so there are clearly environments that may even have life today. We just have to go there and look for it.
Yes.
Yeah.
Lots to explore.
And so our next question, Danny, this is for you on X, from one of our users on X who wants to know, did you find, and forgive me as I pronounce this, pyrimidines or pyrenes or other basic building blocks of life?
Yeah, so I think it's purines and pyrimidines.
Purines and pyrimidines, I appreciate that.
And indeed, yeah, so the 5 nucleobases, we found, adenine, cytosine, guanine, thymine, uracil, right, all 5. And cytosine, thymine, and, oh, there we go, a nice slide, so I don't, and uracil are what are known are pyrimidines. These are pyrimidines. And then the purines, adenine and guanine, you see there. So there are different structures. The purines are a little larger, right? They have these 2 rings, whereas the pyrimidines have single rings. And again, all of these have been discovered in the Bennu samples.
And what is the significance of these molecules, though, when we're thinking about life and building blocks of life?
Yeah, I mean, like we said, these are the genetic components of DNA. This is the genetic code, right? The components of that. So that's the significance. I mean, biology doesn't exist as we know it without this ability to replicate imperfectly and evolve with DNA and RNA and nucleic acids. So this is fundamental, fundamental chemistry here.
And it's mind-boggling that, again, it's found in samples of an asteroid that is currently in space right now. And so, incredible to think about.
Yeah.
Our next question is from Skycracker on Twitch, who wants to know, where can we read about your research if we're interested in learning more? That's a great question. Sarah?
That is a great question. So Danny's team and our team just published papers that came out yesterday in Nature and Nature Astronomy. So you can read the original research there. And it's
open access.
Open access. Anyone
free.
can access it. Yes.
Anybody can. Yep.
Yes. And NASA have picked it up, writing some articles for lay people as well to be able to read.
That's wonderful. Thank you both. My next question is for Danny. So we have Dorian Gray on Twitch, who asks, when talking about the building blocks of life on Bennu, do you mean things that could have led to life or past traces of life?
Yeah, this is a really important, thank you for the question, because let's be clear, we're finding the chemical building blocks, things that could have eventually assembled together, right, to form something that's closer to life as we know it, DNA, RNA, large proteins. We're not finding those complex molecules on Bennu. We're not finding, life itself. We're seeing the building blocks, and there's a long way to go, chemically speaking, to get from the building blocks that we see to life itself. How that happened, how long that took, That's kind of an open question, that we're trying to figure out.
And we have, next for Sarah, we have someone on Twitch who wants to know, why was Bennu chosen for the mission? I know you hit a little bit on this earlier, but I think it's really important to drive home, especially for all the discoveries we've made from the sample.
Yes, so Bennu was chosen because, firstly, it's a near-Earth asteroid, so it orbits around the Sun about the same distance as the Earth does, so that makes it more accessible for an asteroid. It was in the right place at the right time. So that's the first thing. And then secondly, we thought, we were hopeful that this was going to be full of carbon and water just from the measurements we could make from Earth. And we wanted to pick an asteroid like that because we wanted to write the papers that we're writing now. So yes, so we did pick the right asteroid, we did find one that contained water and carbon. So that was really important. And then the final special thing about Bennu is that it actually has a very small chance of hitting the Earth in the very distant future. So that was another...
Very small.
Very small.
Yes.
Very small.
Very small. We should not be worried.
Yes, but that was another reason to go and study it in more detail, to look more closely at its orbit and how that was affected by the radiation from the Sun.
Yeah, I think there's no chance in the next 100 years it could hit. And I think in 2182, there's like a 0.04% chance that it could hit in 2182. So I'm not going to lose any sleep over it. We've got
We've got some time. And so I have that Opal guy on YouTube, Danny, who wants to know, are there any plans to send a mission back to Bennu in the future?
That I currently know. That's a good question. I think part of the thing, I mentioned the drive to explore, and we want to go new places. We want to go to Sirius. We want to go to Comet. We want to go, and we actually have a mission now, Clipper, that's going to go explore Europa, the icy moon of Jupiter. So I think kind of the human tendency is to want to see new things,
stuff,
discover new things.
Enceladus, I'd put that on the list.
Yeah, Enceladus. I mean, God, there's so many places.
Yeah. And so my next question is from one of our followers on Twitch who wants to know, are different teams performing different tests on the sample? So for example, both of your teams performed two totally different, focuses of this sample. Do you know if that's the same for everybody that's getting a piece of Bennu?
Yes, so the way we arranged our analysis was divided up into a few teams. So there's the mineralogy team, which I'm on, organics team that Danny's on.
Cool.
And then we also have a element and isotope team who's doing more of a deep dive into the chemistry. And we have a team that's looking at the physical properties, things like the density of Bennu. And what else do we have? A team looking at the spectral properties. So that's comparing the data we got from the spacecraft to doing very similar techniques on Earth, because that enables us to see how correct we were in our predictions, which will help us look to other asteroids as well.
So we're really studying this from every angle. Now, are your teams talking with each other? And, how does all this information, I guess, come together for the bigger picture?
Yeah, so, communication is obviously important. We don't all work in isolation. You in the lab, but no, we actually have the structure. We have these working group leads. So for each of these groups that Sarah was talking about, we have a lead and we have a deputy. And actually the leads get together and talk about, what we're finding. We have science team meetings. There's one coming up in Tucson next month or end of March. And that'll be another opportunity to discuss the results. Where do we go from here? So that's actually a really important part of this, right? We need to be communicating, sharing our results so we can plan the next steps.
Yeah. So my next question is Angel Lady on Twitch, who asks, are there any specific planets or moons within our solar system that you believe could harbor life based on the ingredients found in the asteroid samples? So
yeah, absolutely. I think the astrobiologist should answer that.
Well, we've talked about them already, right?
Yeah.
Europa, huge ocean, icy moon of Jupiter, and Enceladus, another icy moon of Saturn. And in that case, it's actually spitting out some of this ocean material as a plume. Pretty exciting.
And is it just the water on those two?
Yeah, there's a nice image of these plumes coming out. So this is, probably this stuff's derived from the subsurface ocean. So want to sample that, want to analyze that. It'd an amazing discovery to find life, but I wouldn't be shocked. I mean, this is exactly the kind of environment where life could evolve.
And that's so exciting too. I mean, as you mentioned, we've got Europa Clipper on its way right now to look at the habitability of that icy moon. And so, more to come.
Yeah.
Absolutely.
I have one final question for you both. And that is, what advice do you have to viewers who might be interested in, helping NASA study other worlds like Bennu?
So my advice to everyone is always to follow your heart. And when you're thinking about your career and your career choices, it's so important to do something that you're truly passionate about. Like Danny and I are passionate about what we do. So absolutely, just go for what you really enjoy. But do make sure you take maths classes, though. That's useful for everyone.
Yeah. Math, science in general. I guess one of the big learning moments for me, and I went from physics to chemistry, which are very different, and that was because of that Alan Hills Martian meteorite. But I think, science background's important. Obviously, if you want to study pieces of Bennu, you should like rocks, space rocks. But again, follow your heart, work hard. There are many different ways to get to where we are now. And again, I wouldn't even never dreamed of this as a child. So,
same.
Yeah, here we are.
Well, that's great advice. And thank you so much for being here on this show, and also congratulations on your discovery. I know that it has been decades in the working, right? And you have something so cool to show for. So again, thank you both for your time.
You're welcome.
Thank you.
And thank you all to our viewers online watching today. Now, if you didn't get enough, we have another opportunity for you to speak directly with the scientists involved in the sample return. That's happening tomorrow, January 31st, from 2 to 4 p.m. Eastern on Reddit. We'll have another Q&A, and you can visit reddit.com/r/NASA. Now, to stay updated on Bennu science, you can follow NASA's solar system on Instagram, Facebook, and X. This is one of the first studies of the asteroid material. And as we talked about earlier, there are going to be dozens of investigations going on all around the world and will continue for decades. So be on the lookout for more discoveries as the story continues to unfold. You can read all about the exciting findings from the asteroid sample on nasa.gov/OSIRIS-REx. Thank you, and see you next time.